So in this video we're going to develop the formula for the distance from a point to a line in three-dimensional space. So remember, if you have a line in L in three-dimensional space, that we can give a vector representation for that line by taking a vector to the line. So this just needs to be a point on the line, and then we multiply it by a scalar times a vector parallel to the line. So this is a point on the line, which also forms a vector from the origin to the line, and then we scale it by any vector we want that's parallel to the line. So if we give this guy a name and call him P, and we give the direction vector ABC a name U, then the claim is that if we have a point Q that's not on the line, then we can find the distance from Q to the line by taking the vector from P, the point on the line, to Q, crossing it with the vector U, finding the size of that cross product, and then dividing it by the size of the vector U, where U is just this direction vector right here. So the idea is pretty simple. If you have a line in three-dimensional space, and you've represented it as x sub 1, y sub 1, z sub 1 plus k times this direction vector, you know that if you are in a three-dimensional coordinate system, that this guy right here is just a vector from the origin to the line. And that tells us that x sub 1 comma y sub 1 z sub 1 is just a point on the line. And then if we take a point Q and we call him, and here we're giving him the name P. So here's the point on the line. And if we take a point Q not on the line, it's easy to construct the vector from P to Q. And we know that ABC is a direction vector parallel to the line. So if let me change the color of the pen here, pointer, ink, switch over to black. So ABC is just going to be some vector parallel to the line. And the idea is the vector from P to Q and the vector U, which is just this direction vector right here, they're going to form some angle theta. Maybe I can get a little bit better picture here. They're going to form, let's put Q over here a little bit further. I'll put Q over here. So the vector from P to Q and the vector U are going to form some angle theta. And the idea is if we drop the perpendicular from Q to the line, this distance from Q to the line, we can just get it from trigonometry. If this angle right here formed by PQ and U is the vector theta, then this distance from trigonometry is going to be, hey, here's the vector from P to Q. So if we do the size of PQ, that's actually the hypotenuse of this right triangle. So this distance right here by trigonometry is going to be the size of PQ times the sine of the angle theta, because this is the side opposite theta. And then all we need to do from there, once I recognize that the distance from Q to the line is just the size of PQ times the size of theta, what I want to remember is we've already proven this semester that if we want to know the size of the cross product of two vectors U and V, that the size of the cross product is equal to the size of U times the size of V times the sine of the angle formed by those two vectors. So if we're interested in knowing the length of the cross product of PQ with this vector U, the size of PQ cross U, we know from a previous result that we would just calculate the length of PQ times the length of U and multiply by the sine of the angle between the two vectors. So if we just divide both sides right here by the size of U, we get that the size of the cross product divided by the size of U is the same as the size of PQ times the sine of theta, but by trigonometry the size of PQ times the sine of theta is going to be the distance from Q to the line. So when we want to find the distance between a point Q not on a line and the line, we can use this formula right here, and this is just the justification for why that formula works.